Let's look at one more trick that can make calculating triple integrals easier. So let's try to evaluate the integral of this function, x squared plus z squared, all times y, over the region cut from the cylinder x squared plus z squared equals 4 by the planes y equals 0 and x plus y equals 3. So I guess first we need to figure out what is this region exactly. So this cylinder, right, in the xz plane, it's just a circle. Since y doesn't appear in this equation, that means the full 3D surface generated by this equation is just this circle, but moved in the x direction. So let's put the x-axis going this way, the z-axis going this way, and the y-axis going this way. So x and y, the positive x and y axes are coming out towards you. They are not going into the screen, they're coming out towards you. So in the xz plane, this cylinder is just a circle, so let's draw that circle like this. But then we drag this circle in the y direction to generate our cylinder, so that's going to be like this. So there's our cylinder, and this back edge here is hidden behind, that's why I drew it dotted. Okay, so there's our cylinder. But then we need to cut this cylinder using the plane y equals 0. Well, the plane y equals 0 is the xz plane. So, right, this rear cross section is the cross section at y equals 0. And now we need to slice this with the plane x plus y equals 3. So what does that look like? So we can figure out what that looks like just by drawing what it looks like in the xy plane, right? X plus y equals 3. That is a plane in 3D space, but since z doesn't show up in this equation, we can plot this equation in the xy plane. So that's going to, let's see, y-intercept 3, slope -1. So that's going to look like this. And the 3D plane is what we get by taking this line and moving it in the z direction. So this line looks something like, so I'm going to draw this line going from a point on the y-axis, so here somewhere, to a point on the x-axis. And so the plane is that, but sort of stretched upwards like this. So this plane is slicing the cylinder sort of in a diagonal way, kind of like this. Okay, so what we get is, I'm going to do my best to draw this, so apologies ahead of time. We get this kind of shape. So it has this rear circular cross section, but this front edge is angled, right? It's like a wedge. Would this be any easier to draw if I drew it vertically? For some reason, it's easier to draw this vertically. It shouldn't be, but it is. So this is the shape we're dealing with, right? But reoriented so that it's pointing that way. Okay, well, you can see that no matter how we slice this, the bounds are going to be really gross, right? Every cross section has some sort of curvy weirdness going on, and that's kind of unpleasant. But I mean, if you think about it, because we have x squared plus z squared, and because we have this circle, and because there's x squared plus z squared here, I mean, if it weren't for the fact that we were dealing with a triple integral, this would be a clear case for using polar coordinates, right? Well, we can use polar coordinates. We'll use polar coordinates just for the xz plane, right? Because in the xz direction, those are the things that made us think of using polar coordinates. So let's use polar coordinates in the xz plane. This does involve making a choice. So the choice I'm going to make is that x is r cosine theta, and that z is r sine theta. You could swap these. That might change what your bounds are. It might also change what the integrand is, but it won't change what you get for the value of the triple integral at the very end. Right. So let's figure out what we get. So first of all, we need to deal with our differential. So dv, which is dx, dy, dz. Okay. But if we put the dx and the dz together, like this, well, that's just dA in the xz plane. Right? That's a little patch, an infinitely small patch of area in the xz plane. But we know the relationship between Cartesian coordinates in a plane and polar coordinates in the plane. Right? dx dz, it should be r d theta. So the dy is just like a spectator. It doesn't participate in this change of coordinates. All right. So when we set up this triple integral, we'll still have y floating around, but instead of dz and dx, we'll have r d theta. Okay. It's hard to know ahead of time what order to put these in. If we put y on the outside, we would be slicing so the y-axis is going this way. We would be slicing at constant y values. That would be bad because some cross sections are entire circles, like this one, but when we get far enough to the front edge of this thing, some cross sections are sort of partially circular, but with this flat edge. And that seems bad, right? Anytime your cross sections change their nature halfway through the integral, that's bad. So let's not put y on the outside. Let's put theta or r on the outside. And just out of kind of habit from when we were doing polar integrals, let's put theta on the outside. And then maybe dr inside of that, and then dy. Don't forget the r, right? We need to stick that r somewhere. Now we need to write our integrand in polar coordinates. But remember, in polar coordinates, r squared is x squared plus the other coordinate squared. So this x squared plus y squared right here, this is just r squared. So our integrand is r squared y. Okay, so really we'll have an r cubed because of that extra r. Now we need to think about, okay, what about our bounds? So for theta, if we're sitting at the origin here, let me do it on this. And before I do that, let me clean up this diagram just a little bit. Okay, so if we're sitting at the origin and if we're thinking what directions do we have to go in the xy plane to cover this region? Well, we have to go in every direction to cover this region, so we should go from 0, we should do a full turn, so from 0 to 2 pi, or minus pi to pi, or whatever your favorite interval of length 2 pi is. Okay, now along one of these directions, what r values do we get? Well, right, so we've sort of taken a slice at a certain angle, like this. What r values are there on this slice? Well, from the middle, which is going to be r equals 0, out to the edge here. But the edge is the edge of the cylinder, and the cylinder has radius 2. So r is going to go from 0 to 2. Okay, now we have one of these slices, and we need to know what y values do we get. So along one of these slivers, what y values do we get? Well, the smallest y value is always just 0. That's comforting. It's always nice when that happens. But what is the largest y value? Well, the point that determines the largest y value is on this angled plane. And what is the angled plane? It's this right here. X equals y, x plus y equals 3. So what we want to use for this upper bound is x plus y equals 3, because this is the surface that determines that upper bound. So we can solve this for y, because we're using it as a y bound, so we need to have y equals something. So y equals 3 minus x. But we decided to use polar coordinates for the xz plane, so we need to rewrite x in terms of polar coordinates. And the choice that we made up here is that x is r cosine theta. So we get 3 minus r cosine theta. So that is what goes in our upper y bound here. So 3 minus r cosine theta. Okay, so now that we have that, I'm going to erase this here so that we can do our integral. Okay. Now notice there aren't any thetas for these inner two integrals. There are no thetas. So we can take this entire inside double integral and move it outside of the theta integral, like this. So do our separate our theta integral from our ry integral. Can we do that? No, we can't do that. Sorry, we can't do that because there's a theta in our bounds right here. So we can't do that. Oh boy, I'm glad that I noticed as quickly as I did. Got to be careful with triple integrals. Okay, so we do need to do these integrals one at a time. So integral from 0 to 2 pi, integral from 0 to 2, and now the integral of this stuff, so this is r cubed y, is our integrand. So we're integrating with respect to y, so that's going to give us 1/2 r cubed y squared, and we're going to go from 0 up to 3 minus r cosine theta. You can kind of see the pain that's going to happen already because we're going to have to square that mess. Oh well, that's what we signed up for. That's what I signed you up for, I guess. Okay, integral from 0 to 2 pi, integral from 0 to 2, 1/2 r cubed times, so plug in our upper bound, 3 minus r cosine theta, that squared, minus, and then plug in our lower bound, 0 squared. Okay, now we're going to have to multiply out this squaring to do this integral. So integral from 0 to 2 pi, integral from 0 to 2, 1/2 r cubed. Multiply out this squaring, we get 9 minus 6r cosine theta plus r squared cosine theta, dr d theta. Okay, to do this r integral, we need to distribute this r cubed. So let's distribute the r cubed. That makes this 9r cubed. It makes this 6r cosine theta 6r to the 4th, and it makes this r squared into r to the 5th. Yikes. Okay. Now we can do the r integral. Notice we still can't separate because, well, first of all, this isn't a product, so we still can't separate. So integral from 0 to 2 pi, there's that 1/2 there, and then integrate this, we're going to get 9 over 4 r to the 4th minus 6 over 5 r to the 5th cosine theta plus 1 over 6 r to the 6th cosine theta. This shouldn't be cosine theta. This should be cosine squared theta, right? So I need a squared right here and a squared right here. And then we need to evaluate this from 0 to 2. Okay. So let's slip this 1/2 outside. Integral from 0 to 2 pi. When we plug in our bottom bound, we're just going to get 0. So let's stop worrying about that. Let's plug in our top bound. 9 over 4 times 2 to the 4th. 2 to the 4th is 16. 16 over 4 is 4. So 9 times 4, 36. Right? 36. Okay. 6. Oh man, now the numbers are getting big. 2 to the 5th is 32. 32 times, so 6 times 32 over 5 cosine theta plus, oh man, 1 over 6 times 2 to the 6th, that must be 64, times cosine squared theta. Okay, so I'm not going to do the arithmetic on these constants. The only integral we have left is this theta integral, and all of these things we can integrate with respect to theta. So 36, the integral of that is 36 theta minus 6 times 32 over 5. Integral of cosine is sine theta plus 64 over 6, right? Simplify your fractions, kids, but I'm not going to do it right now. So integral of cosine squared, remember cosine squared is 1/2 1 plus cosine 2 theta. So we get that factor of 1/2, and then the integral of 1 is theta, and the integral of cosine 2 theta is 1/2 sine 2 theta. And so now we need to evaluate this from 0 to 2 pi. Okay. So I'll let you do the final evaluation and clean up the value of all the integrals if you want to. Right, just like when we were doing double integrals, we need to keep our eyes out for opportunities to use what we know about polar coordinates. So in this example, we used polar coordinates for the xz plane, but of course you could use polar coordinates for any pair of coordinate directions, depending on what the situation is. So suppose we wanted to integrate some function, how about xyz, over the region enclosed by, let's say, z equals 4 minus x squared minus y squared, and z equals 0. So we know what z equals 0 is. That's just the xy plane. Z equals 4 minus x squared minus y squared. You might need to look at some cross sections to figure out what shape this graph is. If you make a quick contour plot, you'll see that the cross sections are all circles. In fact, they're like this. So it's one of these upside down parabolic bowl things. Okay. So what is this lowest cross section here? Well, that's the intersection of the paraboloid and z equals 0. So if we plug z equals 0 into the equation for the paraboloid, we get 0 equals 4 minus x squared minus y squared. So that's x squared plus y squared equals 4. So the region in the xy plane that we're looking at the bottom of this, is a circle with radius 2. So we could use polar coordinates for the xy direction this time. So if we do that, let's set this up quickly. So if we use d theta and dr, r dr d theta, so this is taking the place of dx dy. Now we need a dz. Okay, so our integrand was x times y times z. Z is still z, but x is now r cosine theta, y is now r sine theta. Okay, now we need to figure out our bounds. So what about the theta direction? If we're sitting at the origin, in what directions do we need to go to cover this region? Well, every direction, so 0 to 2 pi. Along a single direction, what r values do we need? Well, from the middle out to the edge. So that's from the middle out to the edge. So that's from 0 to 2 in the r direction. And then in the z direction, right, what is the sliver that lives above this one point in the xy plane? Well, the lowest point on the sliver is at height 0, and the highest point on the sliver is on the paraboloid. So the paraboloid is, I need some space here. The paraboloid is 4 minus x squared minus y squared. Oh, but we can't use x's and y's because we switched to polar coordinates. X squared plus y squared, that's r squared. Okay, so now we have a triple integral we could calculate, but we've replaced our x's and y's with polar coordinates for the xy plane. Right, so depending on what your region looks like and what your integrand looks like, you can use polar coordinates for x and y, for x and z, or for y and z, whichever is most convenient.